Hello, we're starting section 5.3, the gas laws. So earlier we talked about some assumptions for ideal gases, and really they are what it says ideal. There aren't any such things as ideal gases, but real gases behave closely enough to ideal gases that all of these equations and using these assumptions works and gives um, very accurate answers. So we know that real gases do have volume and they do lose energy when they collide with things, and there are intermolecular forces involved. They have attractions for other different things. Um, but in but these assumptions do work. Um, so the only the two main times that there are huge exceptions to behaving like an ideal gas is at high temperatures and at low pressures. And if you stop and think about it, okay, when would a gas most likely become the least gas-like it could be? When it's trying to become a liquid. Okay, so how would you make a gas turn into a liquid? Okay, well, you would give high pressure and you would do super low temperatures. So those are the two times where they have trouble. So we aren't going to be discussing any things like that. And when I'm talking about ultra low temperatures, I'm talking about like absolute zero, near absolute zero, or very low temperatures anyway. So I'm not sure how frequent um, oxygen tanks have liquid oxygen in them, or when they have compressed oxygen. But people, with respiratory issues, they do have they do use portable oxygen tanks and things. Some of them are liquid oxygen, and some are compressed air. People really do have to use these equations and calculations and things. So this chapter does have real world applications. So here are more examples of ultra high pressure when they're compressing those gases. If they get those molecules as close together as they are when they're a liquid, then or a solid, then they're not gases anymore and they're not going to behave like gases. Or here's liquid nitrogen in a freezer. So I think it's like negative 75 degrees Celsius or something, or maybe lower than that. I can't remember. So the first law that we're going to talk about is Boyle's law. And Robert Boyle was a Irish scientist um, around the time that the Mayflower and the Pilgrims came to America is when he was born. So during their lifetime and things is when he lived. He was a Christian, and he said that the two great books of nature and of scripture have the same author. So the latter does not hinder at all an inquisitive man's delight in the study of the former. And I think that's so beautiful in light of how things are today. People there's a lot of people that are scientists that try to disprove the Bible. And he was trying to show that they agree. He is known currently as the father of modern chemistry. And in 1660, he was also one of the 12 founding members of the Royal Society of London. Now, that wasn't like a social society, that was a society of scientists. And they're the highest level of scientist in Great Britain. So he was deeply religious, and his faith played a significant role in all of his scientific endeavors. And his writings often reflected his effort to reconcile scientific discoveries with religious beliefs. He was very, he was known for his philanthropic activities. He funded translations of the Bible into various languages and supported missionary work. And his commitment to advancing knowledge and improving society extended beyond the laboratory. And his law was pressure times volume equals a constant. So the pressure and the volume are inversely related. If one goes up, the other one goes down, but they equal a constant when they're multiplied together. And that's if the temperature stays constant. So here's an example, figure 5.8 in your book. So according to Boyle's law, an increase in the pressure on a gas caused the volume to decrease, and a decrease in the pressure would cause the volume to increase. So the opposite effect, assuming the temperature's held constant. So here's a whole range of different volumes and different pressures. Now the temperature stays the same. So notice here the pressure is doubling. So there's 250 torr, 500 torr, 1000 torr. So it doubled and then it doubled again. And the volume reduced by that same, it halved each time. So 1000 to 500 to 250. So they have that inverse relationship. Now, if I get rid of the other two and show this one, so here the pressure tripled, so 250 to 750 torr, and the volume decreased by into a third of what it was. So it keeps that same constant relationship if the temperature does not change. That's the only time his law will work. Pressure and volume are the only things changing. Okay, so if you think about one molecule of a gas in a large flask and then also in a flask that's half the size. So at a constant temperature, that single molecule will have the same kinetic energy in either flask that it's in. It will thus make the same total number of collisions per unit time. But since the smaller flask has a smaller surface area, the number of collisions over a given area per unit of time, the pressure will be greater. It's going to hit the side more often. So it's moving at the same speed, but the surface area, the inside of that container is smaller. And so it is going to hit the sides more often. And that makes the pressure. The more it hits the sides, the greater the pressure will be. So let's talk about solving gas law problems. So it's best to follow these step-by-step directions and format a table and figure out which one of the variables that you're looking for and make sure they're all in the same units and make sure that your answer has the right is reasonable to what you're expecting. So you can look at that equation and tell whether or not something is directly or indirectly related and whether it should be bigger or smaller, when you get the answer. So here's our first question, example 5.3 in your book. A flexible helium-filled weather balloon has a volume of 500 liters at a pressure of 1 atmosphere. What will be the volume of the balloon when it reaches an altitude at which the pressure is only 0.5 atmospheres? Assume the temperature is held constant. So we need to fill out this chart, and they have got it filled out already. So we've got the initial findings. So they told us that the volume is 500 liters and at a pressure of 1 atmosphere. So starting out, the volume is 500 liters and the pressure is 1 atmosphere. What will be the volume? We don't know that yet. When it reaches an altitude at which the pressure is only a half of an atmosphere. Okay. So step 2, Boyle's law states that pressure times volume equals a constant. And since K is a constant, it's always going to be the same value. If we have two whole sets of pressures and volumes, we can set them equal to each other. So since the PV for the initial equals a K and the P times V equals a K for the final, we can make them equal to each other. So the yellow group numbers will equal the green group numbers. Then we fill in the values to calculate, and do not forget the units. So we have 1 atmosphere times 500 liters equals a half of an atmosphere times the variable V for volume. So let's multiply and divide by the 0.5 atmospheres, solve for V. So our unit, the 0.5 atmospheres cancels out on this side. The atmospheres cancel out on this side. And when we divide 500 by a half, we get 1,000 liters is equal to the volume. So when the balloon reaches an altitude at which the pressure is only a half of an atmosphere, the volume is going to be double what it is. So the pressure halved, so we expect the volume to double. So that's a reasonable answer. Then the next law is Charles's law. So it is volume and temperature. Volume divided by temperature equals a constant. So this way, since whatever the volume does, the temperature needs to follow. So if the volume increases, then the temperature will increase, and volume divided by temperature will equal the constant. Or if the volume decreases, the temperature is going to decrease, and this will still equal the constant. So Jacques Charles was a French mathematician, physicist, and inventor. He lived almost 100 years after Robert Boyle. Now, he was a really interesting fellow, and in fact, he was the inventor of the hydrogen balloon. So he thought, after he had seen or heard about a regular hot air balloon with the flame and everything in there, he thought, well, hydrogen's a lot lighter, and if he sealed that in a balloon, it wouldn't require any flame, and he thought it would be a lot safer. He hired two brothers that were engineers, Nicholas and Anne Jean Robert, and they built, they used his design to build the first hydrogen balloon. So they tested one out that didn't have anybody attached to it first, and then after that worked, then they made one with a basket. And he went up several times, and he's known as the inventor of the hydrogen balloon. But in 1795, he was elected to the Academy of Sciences in France, and that was very similar to the Royal Society like that was in England. Anyway, he did a lot of studies about gases and things. The volume divided by temperature equals a constant only if the pressure does not change. I should have said that earlier. Here's the example from your book, figure 5.10 of Charles's law. So if the volume of gas will expand as the gas is heated and contract as the gas is cooled if the pressure is held constant. So here the temperature is increasing across the board. So it starts out at 200 Kelvin, and then 400 Kelvin, 600 Kelvin, and 800 Kelvin. Now, remember, this is in Kelvin. So 0 degrees Celsius is 273 Kelvin. So this is actually negative 73 degrees Celsius right here. So this is actually really cold. But then this is getting hot. So really hot. So now the pressure is held constant. So it's got 2 kilograms of pressure on all 4 of these cylinders. So as the temperature increases, So it goes from 200 to 400, the temperature doubled, and likewise the volume doubles, 250 to 500. Here, if we go from 400 to 800, it doubles, and 500 to 1,000, it also doubles. Or 200 to 600, it triples for the temperature, and 250 to 750, the volume triples. So it's very important to have these units right, because if we had it in Celsius, the math wouldn't work out just right. But in kelvins and milliliters or liters, Charles's law will work fine. And we have to keep the pressure does have to be the same across all the calculations. Now, this figure 5.11 shows the volume of an ideal versus actual gases. So again, the volume is in liters and the temperature is in Kelvin. It does have to be in Kelvin. Now, absolute zero is theoretically the temperature, everything should be a solid, and it's theoretically the coldest temperature that scientists think that there can be. So if a substance is a solid and is not in the gaseous state, it is not going to behave as a gas. So this is a graph of liquid nitrogen, or actually it'd be solid nitrogen at zero, absolute zero. And at some point it would turn into a liquid. And then here at around 75 or 80 kelvins, it would turn into a gas. So that's the condensation point. And from then on, it behaves almost exactly as an ideal gas. And remember, nitrogen gas is a diatomic gas, but it still behaves just almost identical to an ideal gas. On this chart, at absolute zero, the volume of an ideal gas would become zero. But we know that there's no such thing as anything that's a gas at absolute zero. So that little thing has to, correct for real gases. So make sure, it's going to be tricky to remember about the temperature, to make sure you convert to Kelvin. We're comparing to absolute zero, so we have to use Kelvin. So fasten your seat belts and just really, really get ready to buckle down and really pay attention to units. So in the gas laws, the pressure is always going to be in atmospheres. They're going to give us all these different things like torr and millimeters of mercury, and we're going to have to convert it to atmospheres or liters. Sometimes the milliliters will work, but if it's in anything, it's easiest to just use liters. And temperature, they're going to tell us Celsius all the time, and we're going to have to convert it to Kelvin. If you forgot how to convert Celsius to Kelvin, there's no degrees sign on Kelvin, remember. So the temperature Kelvin equals the degrees Celsius. You add 273.15, and that will give you Kelvin. So 30 degrees Celsius, you add 30 to 273.15, and you get 303.15 Kelvin, or just 303 Kelvin. And don't put the degree symbol. Okay, so the last lab day also for Charles's law, we submerged a small balloon in ice water for 3 minutes, followed by submerging it in hot water for 3 minutes. But sadly, we did not really observe any noticeable change in volume. I was hoping for a little bit. Here is a much better, more exciting example from Dr. Michael Ducey at Missouri Western State University.
Okay, so now the next thing that we're going to do to demonstrate Charles's law is we're going to put some balloons into this liquid nitrogen. So I've got a balloon here, and what we're going to do is we're going to put this balloon into the liquid nitrogen and see what happens. We like to call these a portable air container, right? Portable gas container. So let's go ahead. Now the temperature of this gas right now is the temperature in this room, which is about 24 degrees Celsius at this point. And what we're going to do is we're going to see what happens. So you'll see already that the volume of that balloon is decreasing dramatically. And in fact, it looks like it completely, all the gas completely is gone. It's what it looks like. In fact, it's not gone. It is just reduced in volume. So if I take this out and we look at what happens to it when we warm it back up, here, I'll hold it so we can watch. We're going to see that as that gas warms back up, that in fact it was still in the balloon, and it's going to refill the balloon. So it's going to return to its original volume, the volume that corresponded to the temperature in this room. Okay, so there we go. So Charles's law. Now, just to have a little bit of fun, I've got a few balloons. So we're going to see how many balloons we can stuff into this container of liquid nitrogen. So here we go. Now let's warm them up.
So I hope you liked that. I thought it was cool anyway. So moving on, example 5.4 in your book on page 105. Let's use Charles's law to solve a problem. So a balloon has a volume of 1,000 milliliters at 300 Kelvin, which is 80 degrees Fahrenheit. If it is placed in a laboratory freezer with a temperature of 200 Kelvin or negative 100 degrees Fahrenheit, what will its new volume be? So let's look at this table and try to fill it out in advance and make sure that you use the temperatures that are listed in Kelvin. So we have an initial volume of 1,000 milliliters or 1 liter at 300 Kelvin. And then we're going to 1,000 milliliters, 300 Kelvin. And it's going to be placed in a laboratory freezer with a temperature of 200 Kelvin. And we have to figure out what its new volume will be. So let's multiply, fill in our equation. So we have volume divided by temperature equals the final volume divided by the final temperature. And then crisscross multiply. So 300 Kelvin times our variable V is equal to 1,000 milliliters times 200 Kelvin. So let's solve for V, divide both sides by 300 Kelvin, and simplify. So the 300 Kelvin and the Kelvins go away. Then we need to divide 200,000 milliliters divided by 300 is equal to 667 milliliters, and that is our new volume. That will be the final volume if we reduce the temperature to 200. So 200 Kelvin is 2/3 of the original temperature, and likewise, the volume is 2/3 of the original volume. So this answer makes sense. So next in your book, they present the combined gas law. Pressure times volume divided by temperature is equal to a constant. So this is Boyle's law and Charles's law combined. So sometimes this is very handy. Also, this section, this page presents a new vocabulary word that we'll use more, and then I think in the next section. We need to know what standard temperature and pressure is. So it's abbreviated as capital STP, and it just refers to 273.15 Kelvin, which is 0 degrees Celsius, and 1 atmosphere, or 760 torr, as standard temperature and pressure. The next example for using this equation, the combined gas law, is example 5.5. A sample of methane gas occupies 5 liters at 730 torr and 27 degrees Celsius. So I told you they're going to give us all these different units and we have to convert them. So the only ones that we can use is the 5 liters. So we can go ahead and write that in our chart, but we've got to convert the torrs to atmospheres and the Celsius to kelvins. What volume will this occupy at 1 atmosphere, or 760 torrs, when cooled to the temperature of dry ice, which is negative 78 degrees Celsius? So these 3 units are the wrong units, and we've got to convert them to ones before we add them to our chart. Let's do the 730 torr. So 1 atmosphere is equal to 760 torr. So the torrs are going to cancel out, and 730 divided by 760 is 0.961 atmospheres. So we can put that on our chart. Next, 27 degrees Celsius, we need to add 273.15. We get 300 Kelvin, and we can put that on the chart. Now, what volume will it occupy? So we're not going to know the volume yet. At 1 atmosphere, when it's cooled to a temperature of dry ice, negative 78 degrees Celsius. So we need to add negative 78 degrees Celsius to 273.15, and that gives us 195 kelvins. So fill in our chart, the initial side of our equation and the final side of our equation. So we have the pressure times the volume divided by the temperature, and everything is from the first column, the initial starting column. Now we plug in pressure, 1 atmosphere, times the volume, V, we don't know what that is yet, divide it by the temperature, 195 Kelvin. So let's crisscross multiply. So 300 Kelvin times 1 atmosphere times the volume is equal to 195 Kelvin times all these over here. So we ran out of room, so I'm just recopying everything over here. So let's crisscross multiply these things. So we have the 0.961 atmospheres times the 5 liters times the 195 Kelvin equals 1 atmosphere times the 300 Kelvin times the V. And we need to multiply all these things, and we get 937 atmosphere liter kelvins all multiplied together equals 300 times atmosphere times Kelvin times our variable V. Now, don't skip the units, because we need them to cancel out, and whatever unit is left over is the unit for the answer that we are searching for. So that's how we know when we get to the end of our problem. So let's divide both sides by 300 atmosphere kelvins, and we can cancel this out. And then we can cancel out the atmospheres and the kelvins on this side, and that leaves us volume is equal to 937 liters divided by 300. And use your calculator, and that comes out to be 3.12 liters. So, does that make sense? If we have the atmosphere almost staying the same, there's not a whole lot of difference between 1 atmosphere and 0.961 atmospheres. The temperature is not quite half, it's reduced. So if the temperature goes down, what do we expect to happen to the volume? If the temperature goes down, the volume should go down. So 5 liters, and we got 3.12 liters. So it went down proportional to the temperature. So here's all our final answers, 3.12, and it makes sense. The next law that we have is Gay-Lussac's law of combining volumes. So Gay-Lussac was another French chemist, and he lived along the same time as Jacques Charles, and they knew each other. He found that when you mixed volumes of gases, they behaved just like stoichiometry balanced equations. So if two kinds of gases were mixed together and they chemically reacted to produce other compounds, the volume would behave the same as the stoichiometry on balancing an equation. So let's say you had 3 volumes of hydrogen and it reacted with 1 volume of nitrogen. The resulting product would be 2 volumes of ammonia. He did a lot of work, and he's the one, I believe, that was credited with discovering what water was made out of, that there were 2 atoms of hydrogen and 1 atom of oxygen. But anyhow, if you had two volumes of hydrogen gas and 1 volume of oxygen gas, it would produce 2 volumes of water vapor. This went really hand in hand with the next law, Avogadro's law. Now, we talked about Avogadro's number that was named for him. He did not discover Avogadro's number, but he did discover this law. And the fellow Perrin that won the Nobel Prize in chemistry and named Avogadro's law, this is what he was studying, part of what he was studying when he discovered that law. So, no one knows what Avogadro looked like. So if you remember, this image was taken from a death mask of his. So this was probably when he died, what he looked like or something. So it's not probably what he looked like during his lifetime. So his law is equal volumes of gases under the same conditions of temperature and pressure will contain equal numbers of molecules. So V, the volume in liters, divided by the number of moles of the gas is equal to a constant. So on your figure 513 in your book, Avogadro's law, there's these 3 different bell jar vacuums. Pressure is the same in all 3 of them, and they have a volume of 1,000 milliliters. All 3 of these gases are different sizes. See how small argon gas is, and it's a monoatomic gas, whereas the other 2 are diatomic, or this one has 5 atoms stuck together. So they're way different sizes of molecules, but there are exactly the same number of molecules in each volume of gas. So although the sizes of these gas molecules differ, the volume occupied by any of them is negligible compared to the volume occupied by the gas, V. So the temperatures of all these gases are equal, so their kinetic energies are equal. The force exerted by each type of molecule is thus equal. Since the total pressure is the same for each gas, there must be equal numbers of molecules causing that pressure. So previously we briefly mentioned STP, so 0 degrees Celsius, which is 273.15 Kelvin, and 1 atmosphere from page 105. Now it's talking, it gives you a new definition on page 107, molar volume. So molar volume simply refers to the volume that 1 mole of any gas at a STP takes up. So just file this away. Remember that we've talked about this and we'll need it in the future. So a helpful conversion factor for converting between gas volume at STP and moles of gas is 22.4 liters per 1 mole of gas, or 1 mole of gas takes up 22.4 liters. So just write that down and remember page 107. To come back to this, we'll need to know this information in the future. The ideal gas equation. So this is the most handy gas equation, and it's a sum of all of them. It's got Boyle's law, Charles's law, and Avogadro's law, all combined, all rolled into one. Now, the bad news is that R, which is the ideal gas constant, or the universal gas constant, is a whole nother number that we need to learn. R is also equal to, if you solve this equation for R, you get PV divided by NT. So if we filled in the information that we just talked about the how much volume 1 mole of any gas takes up, so we would put 1 atmosphere, 22.4 liters, and divide that by 1 mole of any gas, and 273 Kelvin, and that gives us 0.0821 liter atmospheres divided by Kelvin moles. So this gas constant is what we're just memorize 0.0821 liter atmospheres divided by K moles. And every time we use this equation, we have to plug in this number for R. Now, I was really lucky when I was growing up and I learned this in high school, because everyone in Madisonville, their home telephone numbers started with 821. So to me, this was 0.0 and the first 3 numbers in my telephone number. But I mean, I don't know if anybody's got a birthday on August 21st, or let's see, on the periodic chart, 8 is oxygen and 21 is scantium. I don't know. If you can come up with something, maybe you know somebody who's 8 years old and 21 years old, but you'll need to memorize it. I know it's open book for this chapter or for this class, but in the future chemistry classes, you'll have to memorize it. Let's move on. Example 5.6. What pressure will 0.025 moles of oxygen exert on a 400 milliliter flask at 25 degrees Celsius? So we're going to use our new ideal gas law equation, and we've got to make sure we have the right units, and we're going to fill out this chart. So pressure in atmosphere. So it says what pressure? We don't know that. We're going to have to solve for pressure, and we're going to have to look at the units. So moles is in the correct units. Milliliters needs to be converted to liters, and Celsius needs to be converted to Kelvin. So what pressure? We're solving for that. We have the correct units for moles. the number of moles. Let's convert 400 milliliters to liters. So we need the milliliters to go away, and we need the liters. So milliliters goes in the denominator. We multiply by 1 liter over 1,000 milliliters. The milliliters cancel out. 400 divided by 1,000 liter gives us 0.4 liters. So there we have our volume. Now temperature, we need to add 273.15 degrees Kelvin. We get 298 Kelvin. So now let's plug in our values and use this equation. So pressure, we are going to use the variable P and multiply that by the volume, 0.4 liters. It equals the number of moles times our gas constant times 298 Kelvin. So let's cancel out the moles and the Kelvin and multiply. So we have 0.4 liters times P equals, and if we multiply all those numbers, we get 0.61 atmosphere times liters. Now we need to divide both sides by 0.4 liters, and that's going to cancel out, and the liters will cancel out over here. So P is left by itself. P equals 0.61 divided by 0.4, and our units is going to be atmospheres. So P equals 1.5 atmospheres. So that was a really long section for 5.3, but you're ready. You should be ready to take your quiz, and let me know if you have any questions at all. Thank you, and see y'all soon. Bye.